Okay, hi, this is Namrata. Today we'll be talking about the foundation mastery method, and in today's video we will explore sequences and series. So a sequence is an ordered list of numbers that follows a specific rule or pattern, and each number in the sequence is called a term or an element, and the position of each term matters. Since it's an ordered list, the order is crucial. The terms of a sequence are generally written as A1, A2, A3, all the way up to AN, where n is the number of terms in that sequence. We can also write it in curly parentheses, and this way. They both mean the same thing. This is a more formal way of writing it. So here are some common examples that we use all the time. So we have the sequence of natural numbers, right? So starting with 1, 2, 3, 4, all the way up to n. And then we have the sequence of even numbers, so 2, 4, 6, 8, and this is generally written as 2n. Another common example is the sequence of odd numbers, which is 1, 3, 5, 7, and then this is generally written as 2n minus 1. We also have two special sequences, which we call the arithmetic and geometric sequence. So an arithmetic sequence has a constant difference between its terms. So a good example is the sequence of natural numbers. So notice every term differs from its previous term by 1, right? So 1 plus 1 is 2, 2 plus 1 is 3. So 1 is that constant difference between all the terms. On the other hand, a geometric sequence has a constant ratio, meaning if I were to divide a term by its previous term, I would always get the same ratio. So here we see that 4 divided by 2 gives us 2, and then 8 divided by 4 gives us 2. And so that ratio is constant, which is why this is a geometric sequence. So now we talk about series. So a series is the sum of the terms of a sequence, and this is written in this form. So we have sigma, which denotes sum. A of k means we're finding the sum of the first k terms in that sequence, and then the numbers at the top and bottom represent the limit. So we're starting at 1, so we're starting at the first term, and we're going all the way up to n. So we're summing n terms of a sequence. The sum of an arithmetic series is given by this formula. It is n over 2, 2a1 plus n minus 1 times d. So here a1 is the first term of that series, and n is the number of terms that we are summing, and d is that constant difference. So it's the difference between a term and its previous terms, and that is always constant. Now the sum of geometric series is given by the formula a1 times 1 minus r to the n divided by 1 minus r. So once again, a1 is the first term of that series, and r is the common ratio. So common ratio is essentially the ratio of a term and its previous term. So the second and the first terms, or the third and the second terms, and this should always be the same value for a valid geometric series. Now a small caveat we notice here is when n approaches infinity, which means we're trying to find the sum of an infinitely large set of numbers, and our common ratio is less than 1. So let's say it's 1 over 2. In that case, if we raise 1 over 2 to infinity, it becomes a very, very small number, which can be approximated to 0. And so this term, r to the n, becomes 0, and our formula essentially becomes a1 divided by 1 minus r. And so this is a formula for an infinite number of terms. Now we talk about convergence and divergence. So for a sequence, it is said to be convergent if its terms get closer and closer to a fixed number, which we call the limit, right? So this is how we denote it. We say as n approaches infinity, the limit of our terms is L, so it's a fixed number. So here we have an example. Right? Here, for this sequence, we see that we have n times n plus 3 divided by n squared plus 5n minus 110, and this is a convergent sequence because the limit is equal to 1. Now, how do we find this limit? So, first of all, we can write it this way. We say that the limit as n approaches infinity, and then we have our sequence. Now, what we're going to do here is we look at the different factors we have, or the parts. So we have 3 parts. We have this n, we have n plus 3, and then we have our denominator. So we have 3 different parts that we're putting together, right? What we want to do is we want to take the highest power of each of those parts. So here it's simply n. For n plus 3, the highest power is n. And for this entire denominator equation, the highest power is n squared. And so we simplify it. We ignore everything else and take just the highest powers. And when we divide it, we get n squared over n squared, which is 1. So that's how we know this is a convergent sequence. Now let's look at a counterexample. So this is a divergent sequence because its limit approaches infinity. Now how do we calculate that? Once again, we follow the same formula as before. We write it as limit of n approaches infinity, n squared times n plus 3 divided by n squared plus 5n minus 110. Just like before, we take the highest power term of each factor. So here we have n squared, here we simply have n, and then here we have n squared for the denominator. Now when we simplify this, we are left with limit n approaches infinity, and we're left with an n, because the n squares cancel out, and this becomes infinity. And so since our limit is not a constant number, it is not convergent, but it is a divergent sequence.